please just tell me, what have you observed? This is the best learning process. You look at something while moving or not moving, and you tell yourselves, what have you observed? And then you can remember for the rest of your life. Okay. So first tell me, where are the accelerating charges? Do you see the electric dipole in this movie? Anyone? Here, right? So you see these two bright spots changing their location as a function of time. So that's your accelerating charges. Okay? Great. Now that we know, we have accelerating charges. Do you also see the waves that electric dipole generates? Where are the waves? Taiwanese students are silent. Yeah? So you see the waves propagating. So now that at least you believe me, you need to have accelerating charges in order to generate waves. But can you tell me further, in which direction are the generated waves propagating? Complete silence. Okay, so the charge acceleration direction, let's call it y, and this is x. In which direction or directions are the generated waves propagating in? X. Okay. Don't you think that's something worthy of memorizing? This is telling you, in general, the generated waves propagate in a direction perpendicular to your charge acceleration. Okay. Seeing is believing. I can do all the mathematical derivations for you to prove it, but hey, you have a simulation. This is using Buchla force, simulating electromagnetic waves. So it's 100% correct. Okay. So now that you have learned from looking at the movie, we know that the generated waves are perpendicular to your charge acceleration direction. How can that be useful as an engineer? Okay? Let me just keep one direction, okay? I need some more space. Do you know what I'm drawing? Anyone? What is that? Yeah, Taipei 101. Okay, yeah, 101. Used to be the world's tallest building. Okay? This is something different. Okay? This is Delta building where we are at. These two buildings are very different, right? This one is thin and tall. This one is short and fat. So if you become an engineer working for some telecom company, and your boss wants you to set up Wi-Fi, condenser antenna. So this antenna is giving rise to accelerated charges. That's what antennas do. Okay? So my question to you, again, this is your first job. If you don't get it, you're fired. You take this guy and you install in Taipei 101. How would you install it? In the second day, you're taking the same router and you want to install for Delta building. Remember, we are at the second floor of Delta building. We're very stingy. We don't want computer science to share our signal. So how would you set it up? And we also don't want the nano science guys to share our signal. Okay? So, how would you align the antenna for Taipei 101? Some thoughts. And you have to be more specific. You want to bend it? Okay? So the lady here tells us, for Taipei 101, you better bend the antenna so that P of T is oscillating or making accelerations in this direction. Why? Because she understands the wave propagated or generated propagates in the direction perpendicular to the charge acceleration. So basically, the radiation pattern of that antenna looks like a donut, the cross-section of a donut. Okay? It's a pity. In the past, we had a Mr. Donut in front of our main gate, no longer, because you don't like electromagnetics, so you're not eating enough donuts. Okay? So, usually, if you only have one Wi-Fi router, you want to work for Taipei 101, which floor would you install it in? The 51st, right? Well, if Taipei 101 really has 101 floors, it's floor 51. What about Delta building? How would you install the Wi-Fi device for Delta building? Remember, computer science, we're not sharing. Okay? How do you do it? You want to align this way, right? Okay? To make sure the computer science people cannot share our signal, low frequency, right? Why? Low frequencies, the ground is acting like conductors that reflect signals. So you have to put water on the floor. Remember? Okay, so that's a trick. So this is a very practical issue. If you understand how waves can be generated, then you appreciate these antennas on that Wi-Fi router. Okay. A question, further enhancing your curiosity. Well, in the past, when I was in undergraduate studies, if I buy this router, it comes with one antenna, and then 10 years passed, people added one more antenna. Nowadays, you spend 1,000 NT, they come with 4 or even 5 antennas. Can you tell me why? Each antenna is able to create accelerated dipole. So each antenna can radiate electromagnetic waves. So why 1, 2, 3, 4, 5? Why do we want to have so many antennas? Think about it. You are going to be future engineers. Think about it. Why would you want to have multiple antennas? check. This is a very popular term. Beamforming. If you have one antenna, you have one wave source. If you have a second antenna, what can you do? This is something you learned in high school. If you have two or even more sources, what can you do? There is a professional term starting with I and ends with E. I'm such a nice teacher. So we are now learning English. Anyone? Interference. Excellent. Interference. Right? Interference. If you have multiple sources, they can interfere. Once they interfere, they can create constructive patterns or destructive patterns. This is something you learn. Young's single slit, double slit experiments. 杨氏单狭缝双狭缝实验, right? So you have constructive bright spots and destructive black spots. So one day, if you decide we're not stingy anymore, we want to share the signal with computer science and nano. If you have two antennas, one can be aligned in this way for us. The next one, you align it here, so all the other floors can use it, right? And if you have multiples aligned, you can shrink the coverage space, right? Only a single desired direction is having strong constructive interference, and all the others are having destructive interference. Okay? Think of the customers. When you buy an equipment with the same $1,000, but it comes with 5 antennas, do you think it's more worthy buying? Right? 5 against 1. It's cool. Think about it, the usage. All right? So now I want to come back to how waves really propagate in material. If you still remember, material gives rise to dipoles. Right? Electric materials give rise to electric dipoles. Magnetic materials give rise to magnetic dipoles. If we only focus on the electric dipoles, then we have refractive index. Okay. Now, again, the very last class really comes to your ability to observe truth from movies. So take a good look. You have the same wave propagating in 2 different materials. On the top, this wave is propagating in something. On the bottom, this wave is propagating in vacuum. Take a good look and tell me what you observe. Are you able to tell me immediately, just by looking at the movie, which part is the wave propagating in vacuum? Top or bottom? Bottom. Why? Because the wave is faster, right? We talked about a wave propagating in material, the speed would be reduced. So here, Okay, yeah, super fast, right? Super fast. And here on top is slower. Why? Why waves propagate at a slower speed in materials? So let me give you a live example, or maybe not live. You come from your dorm or where you live to the classroom every day, assuming every day. Okay? And usually when you park your bike, you park your motorcycle, and you walk to the classroom, as you walk, when you don't encounter anybody, you are like the wave propagating in vacuum. You're super fast. Right? So from the position you start into the classroom, you spend 1 minute and you arrive at the classroom. But what happens today? As you park your motorcycle and you start walking, you see a good friend. Or you see two friends. Okay? First you see a not so familiar friend, you wave and say hi, and you just walk by, right? So what does that mean? So your first friend is like you are propagating in certain material with refractive index 1, N1, okay? You don't really know she or he, so just wave your hand. So you slow down for 1 second. And then you meet a very, very good friend. So what do? As you're walking, he or she is coming, and you stop, and you start to chat. Right? You stop. And you begin to communicate, so that can be represented as a second material giving rise to N2. So N2 is greater than N1. Right? So just imagine, if you are a wave, you are traveling in a material with high refractive index. What does that mean? That means this wave loves this material. Why does a wave love this material? Because this material likes the wave as well. This material responds to this wave. In a sense, the material creates a lot of induced dipoles, right? So the more muddy they are, okay, the more electric dipoles the material can induce. The more electric dipoles induced means each dipole is talking to the wave, right? So when you're talking, when you're really communicating in a very sensitive, intimate way, the wave slows down. Okay? So this is another way you can appreciate refractive index, or the square root of x on y. So try to appreciate whenever you have a very high refractive index. In a microscopic sense, this is telling you this material likes this wave, so it generates a lot of induced dipoles to communicate with this wave, and therefore slows this wave propagation speed down. I don't know whether I should go into the further details. Frequency dependence is, let me skip the frequency dependence for today. Okay, if you're interested, you can take another course. It's called Introduction to Optoelectronics. So usually people include the frequency response into that course. So usually we don't talk about frequency response here, because when I'm teaching that course, just to explain the frequency dependence, it's called dispersion. It takes 2 weeks full. Okay? So let me just stop here. I think you are already exposed to a lot of difficult concepts. So do you have questions up to now? I'm trying to relate the fact of induced dipoles to refractive index and to the speed of the wave in given material. Okay? And using a simple, understandable concept. Right? So are there questions up to now? Yes?
然后聊天是什么？
聊天 generating dipoles. Right? So here, this wave is coming in, so it starts to talk. When a wave starts to talk with the material, it's like you're generating a dipole. So your energy of the wave is actually transferred into the oscillation of your dipoles. So sometime when you have enough chats, okay, this is going deeper. So the real process is the wave comes in, start to induce an electric dipole. Electric dipole is having the electrons being oscillated. So that energy is coming from your wave. Sometime after when you're finished, the dipole stop oscillating, and that stopping re-radiates your wave. Okay? So you think about the wave propagation in material is a sequential of energy transfer from fields into the oscillation of electrons, and then the electrons stop oscillating, re-emit the wave, and the wave propagates for a certain distance, and again starts to talk. Okay? So it's a serial, this energy transfer from field to oscillation, re-emitted field, and talk. Okay? So the talking is converting the energy from the fields into the oscillations. Right? So this is your very good friend. Right? You meet 100 good friends between the parking lot to your classroom. That means you always miss your class. If you don't, you only meet so-so friends, you walk very fast. And that is really frequency dependent. Let me talk about frequency dependence in one sentence. Frequency dependence is a measure of your muchness. If you have a very close friend, meaning your frequencies are in tune, in resonance. Right? In resonance, 共振. So your frequencies are very similar. Then you're trapped. You stop and talk forever for 1 hour, and you miss your class. But if your frequencies are not in tune, so you're out of resonance, you walk by each other very fast. Okay? So I gave you the complete picture of, this is called wave-matter interaction. How wave and materials interact. Right? So you have a sequence of light absorbed and light emitted processes. Right? Any more questions? You ask one question, you get more stories.